Backtracking algorithms, n-queens, sum of subsets, graph coloring, and Hamiltonian cycles. Welcome to this lecture on backtracking algorithms. In this lesson, we are going to study one of the most fascinating problem-solving techniques in computer science, known as backtracking. Backtracking is not just an algorithm, it is a strategy, a way of thinking about problems where many possible choices exist, but only a few choices lead to valid solutions. Whenever we encounter problems involving combinations, arrangements, puzzles, or constrained searches, backtracking often becomes one of the most powerful approaches available. Famous problems such as the n-queens puzzle, Sudoku, graph coloring, Hamiltonian cycles, and many optimization problems rely heavily on this technique. In this lecture, we will first understand the general idea behind backtracking. Then, we will explore 4 important applications: the n-queens problem, the sum of subsets problem, graph coloring, and Hamiltonian cycles. Let us begin with the fundamental concept. Imagine you are walking through a huge maze. At every intersection, you have several paths to choose from. You select one path and continue moving. If at some point you realize that the path cannot possibly lead to the exit, you do not continue wasting time. Instead, you return to the previous intersection and try a different path. This process of moving forward, checking feasibility, and returning whenever a dead end is reached is exactly what backtracking does. Backtracking is essentially a systematic trial and error method. However, unlike brute force search, which blindly examines every possible solution, backtracking is intelligent. It abandons unpromising paths as soon as it realizes that they cannot lead to a valid solution. This pruning of unnecessary search paths is what makes backtracking much more efficient than exhaustive search. Most backtracking problems can be represented as a sequence of decisions. Suppose the solution is represented by n variables. We denote them as x1, x2, x3, and so on up to xn. Each variable can take values from a finite set. Instead of generating all possible combinations at once, backtracking assigns values one variable at a time. After assigning a value, it checks whether the current partial solution is still valid. If the partial solution violates any constraint, the algorithm immediately abandons it and backtracks. Otherwise, it proceeds to assign the next variable. This process continues recursively until either a complete solution is found or all possibilities are exhausted. To visualize this search process, computer scientists use a structure called the state space tree. The state space tree represents every possible state of the problem. The root node corresponds to an empty solution. Each level of the tree corresponds to the assignment of one variable. The children of a node represent different choices for the next variable. Some nodes are called live nodes. These are nodes that have been generated but not yet explored completely. The node currently being expanded is called the E node, or expanding node. Some nodes become dead nodes. A node is dead if all its children have already been explored, or if it is impossible for that node to lead to a valid solution. Dead nodes are pruned immediately. This pruning is the key strength of backtracking. There are 2 types of constraints in backtracking problems. The first type is called explicit constraints. Explicit constraints specify the set of values that each variable can take. For example, if a variable can only take values from 1 to n, that is an explicit constraint. The second type is called implicit constraints. Implicit constraints specify the relationships among variables. For example, in the n-queens problem, 2 queens cannot attack each other. This restriction involves multiple variables and is therefore an implicit constraint. Backtracking works by enforcing both kinds of constraints simultaneously. Whenever a constraint is violated, the corresponding branch of the search tree is discarded. Now, let us study the first and most famous application of backtracking: the n-queens problem. The n-queens problem is a classic puzzle. The objective is to place n queens on an n by n chessboard. such that no two queens attack each other. Remember how a queen moves in chess. A queen can move horizontally, vertically, and diagonally. Therefore, two queens cannot share the same row, the same column, or the same diagonal. The challenge is to place all queens while satisfying these restrictions. To solve this problem using backtracking, we proceed row by row. Suppose xi represents the column position of the queen placed in row I. For example, if x3 equals 4, it means the queen in row 3 is placed in column 4. The explicit constraint is simple. Every queen must occupy one of the columns from 1 to n. The implicit constraints are more interesting. No two queens should be in the same column, and no two queens should lie on the same diagonal. Whenever we attempt to place a queen, we check these conditions. If a conflict occurs, we reject that position immediately. Let us understand this with the 4 queens problem. We begin with row 1. Suppose we place the queen in column 1. Now we move to row 2. Column 1 is not allowed because it shares the same column. Column 2 is also not allowed because it lies on the same diagonal. Column 3 is safe. Therefore, we place the queen there. Next, we move to row 3. We try column 1. It conflicts with the queen in row 1. We try column 2. It conflicts diagonally. Column 3 conflicts with row 2. Column 4 also conflicts diagonally. All possibilities fail. Therefore, we backtrack. We return to row 2 and try another column. Suppose we place the queen in column 4. Again, we move to row 3. This process continues. Eventually, the algorithm discovers a valid arrangement. One of the solutions is 2, 4, 1, and 3. This means the queens are placed in row 1, column 2, row 2, column 4, row 3, column 1, and row 4, column 3. Another solution is 3, 1, 4, and 2. Backtracking systematically explores these possibilities while discarding invalid arrangements early. This is why it is much faster than brute force. Now, let us move to another important application, the sum of subsets problem. Suppose we are given several positive numbers. We are also given a target sum m. Our goal is to find all subsets whose elements add up exactly to m. At first glance, this appears simple. However, if the number of elements is large, the number of subsets grows exponentially. Backtracking helps us avoid exploring impossible combinations. We represent the solution using binary decisions. For every element, we decide whether to include it or exclude it. If xi equals 1, the element is included. If xi equals 0, the element is excluded. As we move through the list, we keep track of the current sum. If the sum becomes greater than the target value, we immediately stop exploring that branch. Similarly, if even after including all remaining elements, we still cannot reach the target, we abandon that branch as well. This intelligent pruning saves a tremendous amount of computation. Let us consider an example. Suppose the weights are 5, 10, 12, 13, 15, and 18. The target sum is 30. We begin by selecting 5, then we include 10. The current sum becomes 15. Next, we include 12. The sum becomes 27. Now, if we include 13, the total becomes 40, which exceeds the target. Therefore, this branch is discarded. We backtrack, we exclude 13, we try 15. Again, the sum exceeds 30. That branch is also discarded. Eventually, the algorithm finds the subset consisting of 5, 10, and 15. The sum is exactly 30. Another solution is 5, 12, and 13. Yet another solution is 12 and 18. The beauty of backtracking lies in the fact that it avoids exploring enormous numbers of impossible combinations. Now, let us discuss graph coloring. Graph coloring is another classic backtracking problem. Suppose we have a graph with several vertices connected by edges. Our objective is to color the vertices using at most m colors. The important condition is that no two adjacent vertices should have the same color. This problem has many practical applications. It is used in timetable scheduling, register allocation in compilers, wireless frequency assignment, and map coloring. In the backtracking approach, we color the vertices one by one. For each vertex, we try all available colors. Whenever we assign a color, we check its neighboring vertices. If any adjacent vertex already has the same color, we reject that assignment immediately. Otherwise, we proceed to color the next vertex. Let us consider a graph containing 4 vertices arranged in a cycle. Vertex 1 is connected to vertex 2. Vertex 2 is connected to vertex 3. Vertex 3 is connected to vertex 4. And vertex 4 is connected back to vertex 1. Suppose we have 3 colors. We assign color 1 to vertex 1. Now, vertex 2 cannot use color 1. Therefore, we assign color 2. Next comes vertex 3. Since it is adjacent only to vertex 2, color 1 is valid. Finally, vertex 4 is adjacent to both vertex 1 and vertex 3. Therefore, it cannot use color 1. Color 2 becomes a valid choice. Thus, one valid coloring is 1, 2, 1, 2. Backtracking can generate all such valid colorings systematically. Now, let us move to the final application, Hamiltonian cycles. A Hamiltonian cycle is a cycle in a graph that visits every vertex exactly once and returns to the starting point. This is one of the most famous problems in graph theory. Unlike ordinary cycles, a Hamiltonian cycle must include every vertex exactly once. Finding such cycles is computationally challenging because the number of possible paths grows extremely rapidly. Backtracking provides a natural solution. We start from a fixed vertex. Then we choose the next vertex among its neighbors. Before accepting a vertex, we check 3 conditions. First, there must be an edge connecting it to the previous vertex. Second, the vertex should not have been visited before. Third, if it is the last vertex in the path, it must have an edge back to the starting vertex. If any of these conditions fail, we reject the choice immediately. Otherwise, we continue recursively. Let us consider a graph with 5 vertices. We fix vertex 1 as the starting point. Next, we choose vertex 2, then vertex 3, then vertex 4. Finally, vertex 5. Now we check whether there is an edge connecting vertex 5 back to vertex 1. If such an edge exists, we have found a Hamiltonian cycle. The cycle becomes 1 to 2, 2 to 3, 3 to 4, 4 to 5, and finally back to 1. If the closing edge does not exist, we backtrack and try alternative paths. This process continues until either all Hamiltonian cycles are found or every possibility has been explored. The Hamiltonian cycle problem beautifully illustrates the power of backtracking. Even though the search space is enormous, the algorithm intelligently eliminates invalid paths long before they become complete solutions. Let us summarize this lecture. We began by understanding backtracking as a systematic trial and error strategy that builds solutions incrementally and abandons impossible choices early. We studied the concept of the state space tree, including live nodes, dead nodes, and expanding nodes. We explored explicit and implicit constraints, which define and restrict the search space. Then, we examined 4 important applications. The n-queens problem demonstrated how backtracking places queens safely on a chessboard. The sum of subsets problem showed how subsets are selected while avoiding unnecessary searches. Graph coloring illustrated how vertices can be colored under adjacency constraints. Finally, Hamiltonian cycles demonstrated how complex graph traversal problems can be solved through intelligent exploration and pruning. Backtracking is one of the most elegant techniques in computer science because it combines recursion, constraint checking, and intelligent search into a single framework. Although the worst-case complexity of backtracking algorithms is often exponential, their ability to prune large portions of the search space makes them practical and powerful for many real-world problems. Thank you for listening, and in the next lecture, we will continue exploring more advanced algorithm design techniques and their applications.